middle of discussing asymptotic properties of estimators. So let me remind you what we talked about last time. So we talked about first order asymptotic properties or consistency of estimators, basically. So if you have a sequence of estimators, you would say that the sequence converges, is consistent for parameter theta naught if the sequence converges in probability to theta naught as n goes to infinity. And the assumption, underlying assumption usually is that, let's say x1 up to xn are IID from some model who's parameterized by, who is parameterized by some parameter theta naught. And so there's a sequence of estimators converges to the true parameter. They need not necessarily be IID, but the models have to be somehow indexed by n, and that would allow you to let n go to infinity. Generally, in this course, we usually think about the IID case. There are some homework problems, perhaps, that look at dependent cases, but so in our discussions, the main focus will be on the IID case. And so last time we proved a result that said that if you have a sequence of estimators that are maximizers of some random sequence of random functions, mn theta, as long as we have these two conditions, the uniform convergence of mn theta to some target function m here is a fixed function, and so uniform means the L infinity norm, the supremum norm, this guy basically, if you recall. So the supremum norm converges, and we talked about the idea that point-wise convergence might not be enough for the convergence of minimizers or maximizers. So what we did last time was to state this result, that if you have this condition, and the additional condition that the target function basically has well-separated maxima. And this condition is slightly stronger than the theta naught being the unique maximum of m. So the corner case is the case where the function sort of asymptotically comes back to achieve the maximum. So you want to rule out that case. So this is a technical condition, we discussed it. And I'll talk a little bit more about it. If the parameter space is compact, it would be equivalent to saying that theta naught is a unique maximum of m. But if the parameter space is unbounded, then this is sort of needed. So under these two assumptions, we proved that theta hat n would be consistent for theta naught. And the idea was using the basic inequality. I'm not going to repeat it, but it's a very useful argument. It's fairly simple, and I encourage you to go through it and try to understand it and reproduce it for yourself. The basic idea of this proof basically recurs throughout theoretical statistics. And so similar ideas have been used to prove consistency of various estimators. We'll see some, for example, 200C, for example, consistency of the lasso in high dimensions, which is quite different from the classical statistics. It uses similar ideas, like start from a basic inequality argument and then manipulate to form these differences from the mean, and then control these differences uniformly in some sense. And then sort of have a lower bound on the other side, which is deviations of the target function from the truth. You want to lower bound it by sort of a distance of your choice. And so that's where the second condition comes in. Okay. So there are, so any questions about the statement of that result? So we went through some of the questions in the office hours last week. So one of the questions was, what are some concrete sort of arguments that allow us to prove something like that. And so I have left the discussion of how to actually prove this, because this is a very, let's say, interesting and quite, let's say, there's an extensive literature. So you could talk like teach basically an entire course on this. So these go under the name of uniform laws of large numbers. And so we saw that in the case of the M estimators, the pointwise convergence was an instance of weak law of large numbers. So for every theta, for example, this function mn theta would converge to m theta by the weak law of large number. So what you want to do is to upgrade that to uniform convergence. So these are collected under the title uniform law of large numbers. And the general idea is that I would prove something like, I want to prove something like that. So you have, let's say, an average of empirical average of a function f applied to x1 up to xn, and x1 up to xn are IID. And then this average is going to converge for every fixed function to the mean. That's the weak law of large numbers, assuming that the mean exists. So the uniform law of large number, or uniform laws of large number, try to prove that the supremum of this deviation over some class of functions, as f varies in some class of functions, this goes to 0 as well in probability. And so if you take that class, for example, in this case, to be m theta of, let's say, x, so as theta varies, so this class would give you the uniform convergence that you need for the M estimators to plug into this theorem to prove the convergence of the M estimators. So some basic conditions are, for example, given in chapter 9 in Keener, Theorem 9.2, you're welcome to take a look. So for example, if the underlying parameter space is compact, if this theta maps to m theta of x is continuous for almost every x, and if there's sort of infinity norm of the m function. So here, this just means this. So if this expectation is finite, which is a very mild condition, then that uniform condition holds. So Keener goes through a proof. Basically, under compactness, things are simplified. Under compactness, the second condition also simplifies. So if m is continuous, omega is compact, then that condition is equivalent to m having a unique maximizer over omega. So in general, so this is the easier condition. This is the more technical condition. The uniform convergence in general, the difficulty is how big of a parameter space we have, or how big of this function space we have. So these uniform laws of large number usually reduce to like pointwise convergence plus some bound on the complexity of this function class. So if things are compact, you can sort of cover a compact set by a finite set of balls. Let's say things sort of reduce to the finite case. But in general, if your f is sort of infinite dimensional, then you want to cover it with enough balls so that you pay a small approximation error price. And so the complexity of that function class comes in. And so there are a lot of interesting results in this area. And at some point, we'll talk about this in one of the courses, let's say machine learning or statistical learning theory. And some of the ideas in 200C can also be used. But I'm going to skip this for the purpose of this course. So we'll leave it at this. Okay, questions? So this is a little bit of an argument for why compactness is enough for condition B. So if you're interested, you can go through it, or you can try to prove it yourself. Let's see if you have any questions. No questions? All good. Okay, so for example, let's try to apply this result to the MLE. So we saw that the MLE is obtained as an M estimator with m theta of x being log p theta of x, here I'm replacing it with log p theta of x divided by p theta naught of x. So this we can't implement in practice, so you can't optimize 1 over n, say argmax theta in omega 1 over n m theta of x, xi, sorry. If I have something like this, where m theta of x is log p theta of x divided by p theta naught of x, I can't implement it in practice because I don't know theta naught of x, so I don't know theta, m theta. But the claim is that nevertheless, the solution would still be the MLE. Okay? Anyone wants to argue why that is true? So although I don't know theta naught here, what I'm saying is that even if I take m theta of x to be this, the solution is not different. So the argmax is not different from the case where I just take this to be the log of p theta of x, which would be the MLE. Why is that?
Is it because, well, p theta naught of x is basically some constant, and so you're basically like subtracting log p theta naught of x, which is just translating the function down, but the shape is still the same.
Great, yeah. So this is just constant as a function of theta. So you'd have like this summation would be 1 over n summation log p theta of x plus 1 over n sum I from 1 to n, or minus 1 over n sum I from 1 to n log p theta naught of x. And that term is constant. So you're shifting the objective function by constant. So the maximizer is not going to change. So the MLE is still a solution of this, and this is more convenient for theoretical analysis. So because the solution of the problem still is the MLE, whatever I get about the solution of this, if I show that this M estimator, sort of M estimator is consistent, then the MLE is consistent. So what do we need here is that the uniform convergence holds, which I'm going to assume that it holds, assuming that let's say, conditions are true. Let's say omega is compact, m theta is continuous. I mean, it depends on what p theta is, but let's say for sufficiently well-behaved models, this is true. So I'm going to focus on the second condition, which is saying that the true parameter is sort of almost the unique maximizer of m theta. So to compute m theta, I have to take an expectation of this guy under the true parameter. So if we do this, this would give me this integral. Okay, so if you write it down, just plug this in here. And when I take the expectation under theta naught, I have to take the integral with respect to this density. And so this is called, so this integral, so there's a negative sign, but this integral is called the Kullback-Leibler divergence between this density and this other density. It sort of is like a square distance among these densities. It's not a square of a distance metric, or a distance doesn't satisfy the property. If you take the square root of this, it's not going to be a proper metric. For example, it doesn't satisfy triangular inequality. It's not symmetric, but it has a property that it's not negative, and it's zero if and only if the two densities or the two distributions are the same. So in that sense, it can be used to measure how far or how different two densities are. So what this is saying is MLE is going to be consistent. What we want is if this is, because there's a negative sign, it's not negative. This is not negative, and this is the negative of it. This could be at most zero. So if the Kovac divergence is strictly positive, then m theta would be strictly less than 0. So the maximizer, or the maximum of this is 0, and it's achieved at theta naught, and it's only achieved at theta naught in the sense that for any other distribution, it's going to be strictly, this is going to be strictly positive. And this is this property of the KL divergence. So we're almost there. So what we need is a little bit more than uniqueness, but you can show this so-called strong identifiability sometimes holds. So you can show that for a proper increasing function, in most well-behaved models, this D is lower bounded by a function of continuous increasing function, or strictly increasing function of the distance of theta naught and theta. And so this forces you to have that condition that you need. So I'll leave something like this as an exercise for you. But up to this point is almost there. But if your parameter space is compact, then you don't need to worry too much about the rest. But otherwise, you can try to prove that condition directly by showing that there is a sort of a lower bound of this form. This is not easy to show in general, but these are the things that you need to translate from the KL divergence, which is basically related to this guy. This appeared in one-sided inequality, if you remember. So you want to lower bound this by a function of the distance, and you need some sort of an inequality like this. Okay, so see the way we define it. It's a little bit different, but yeah. So questions, comments?
Professor, I have a question.
Yeah.
So does that mean when the KL divergence go to 0, then the estimated distribution actually is the same as if we evaluate the MLE? So is that yeah? So
that's a little bit tricky. So it's not. So what this is saying is, if you, let's go back to the proof here. What we ended up showing is that for the M estimator, this quantity goes to 0, right? And
yeah.
this would be the KL divergence between, so in the context of, so let me go back maybe down. Where should we go? So remember this, I'm going to repeat this here. Let me do it here. Okay, so what we showed was that m theta naught minus m theta hat n is less than or equal to, let's say, twice mn minus m infinity, and let's say we know that this going to 0 in probability. So this side is going to 0 in probability, and for the MLE setup, so you can see m theta naught is basically 0. The way we defined it, if you plug in theta naught, would be 0, and m theta naught hat would be negative d p theta naught and p theta hat n. So without that this B condition, the second condition, what that argument shows is just that the KL divergence between p theta naught and p theta hat n goes to 0 in probability, where theta hat n is the MLE. So true even if condition B does not hold. So condition B allows you to translate this back to the theta domain, the distance of theta naught and theta hat goes to 0. So now what is your question?
So then basically I can get a conclusion here that there is a one-to-one correspondence between the point that the KL divergence equals 0 and the MLE estimation, right?
No. So what this is just saying is that if you compute the MLE, and if you look at that density of your model at the MLE, the distance of that density to the true density is going to 0 in the KL divergence. There could be other estimators whose, when you look at, like, there could be, for example, there could be another sequence of estimators, method of moments estimator or whatnot, theta tilde of n, such that d p theta naught p theta tilde n also goes to 0 in probability. So this is not saying anything about uniqueness. There could be many types of estimators whose, when you compute the density, the KL divergence goes to 0. Many Bayesian approaches basically allow you to do something like this.
I see. So basically, yeah. So basically, so MLE is just one type of approach that can make the KL divergence to 0, but it's not the unique.
It might not be necessary. Yeah. So it's a good point that this is like this is designed basically to minimize the KL divergence because of the way the M is constructed. So the MLE is very naturally suited for minimizing KL divergence, or not minimizing, but being consistent. So you can say this is consistency in the KL divergence of the densities. So if your parameter is actually the density, you can think of your parameter as just the density. So you're consistently estimating the density in the KL metric or divergence. But there could be other estimators, yeah. So what this part is saying is that at equality, there is uniqueness, but there could be many sequences for which the KL divergence goes to 0. There's no uniqueness among the sequences that make KL divergence small, right? So yeah, you can't just say only the MLE has this property that the KL divergence of P theta hat n converges in the KL divergence to 0.
I see.
Right?
Yes. Thank you.
Good. No problem. Other questions? Okay, this was a good point. Yeah, I can talk more about this, but let's leave it at that. So in the exponential family, the KL divergence has a very interesting property. So if you write down the KL divergence in the exponential family, you get back the so-called Bregman or Bregman divergence that we encountered briefly in one of the examples. For example, if you do the exponential distribution, which is a very special case of an exponential family, if you write down the KL divergence between, let's say, p theta lambda and p lambda, lambda was the rate here, then you get this quantity, and this is what we encountered. This is the Itachi-Saito distance. And if you recall, we used this as a loss function in one of the earlier examples that we did to show that the optimality properties in decision theory are tied to the loss function. So if you change the loss function, something that was admissible could become inadmissible and vice versa. And this was a Poisson sort of rate example, estimation of the Poisson rate, Poisson process rate example. And so this Itachi-Saito, which we just wrote down, just comes out as like a KL divergence in the exponential exponential distribution family. And in general, if you write it for general canonical exponential family, you would get a Bregman divergence associated with the log partition function. And so I'm just going to leave it at that, and you can verify for yourself. Just write down the KL divergence in an exponential family. And as usual with the exponential family, everything has a special form, a special name, special meaning. And in this case, there's no wonder that the KL divergence also turns out to be something interesting. It has been already named in a different context. Okay, so this is a valid loss, for example. You can verify from the properties of KL divergence that this has to be non-negative, is exactly 0 when lambda is equal to 0. And So as all the nice properties of a loss function. Okay, questions, comments? Okay, if not, let's see how far we can go now. So now I'm going to talk about the second stage in asymptotic analysis classically. So once you prove that your estimator is consistent, you can try to understand a little bit more by asking how fast you're converging to the true parameter. And this is where comparison of estimators come in. So in asymptotic theory, basically how fast you converge tells you how good your estimator is, because it sort of shows you how the variance or the distance to the truth is reduced as a function of the sample size. So the good estimators would converge fast. The bad estimators would converge slower. And so the rate of convergence sort of tells you which one is better. And so traditionally, so let's look at like the simplest example, because you have x1 up to xn. So it should be x2 up to xn. These are IID, it means mu, and the covariance, let's say, sigma, covariance matrix sigma. So by the weak law of large number, we know that the sample mean converges in probably to mu. So this is the probability sort of world. This is the statistics world. So this can be restated as a statistics fact that x bar n is consistent for mu. That's another restatement of weak law of large number. So the sample mean is consistent for estimating the population mean. And this is a consequence of the weak law of large number. Now I can ask how fast it converges to mu. And the way traditionally this has been worked out is that we showed that root n times x bar n minus mu, this converges to something constant, more or less. But it's not going to be converging to something specific. Things are sort of random. What happens is that if you properly rescale the error, so if you multiply it by a large enough number, if you multiply by a small number, the result still goes to 0. If you multiply by a very big number, the result goes to infinity. If you multiply it by just the right number, the fluctuations sort of stabilize in the sense that they neither go to 0 nor to infinity, but they just fluctuate around 0, let's say. And this is the restatement of the CLT. So if you rescale this deviation by root n, it turns out that this rescale deviation converges in distribution to a normal random vector, which means 0 and in covariance sigma. And this just says that this is the right rate of convergence. We'll go over this a little bit more carefully later. But what you would this shows not only that you converge at a rate which is 1 over this basically, so you converge at the rate 1 over root n, and it tells you something about the sort of statistical properties of this rescaled fluctuation. So it's gonna, for example, in this like univariate case, this would be normal 0, 1, and so the fluctuations would be around like a band of -2 and 2 with probability 95% or 0.95. So you can have built confidence intervals and so on. We'll see that. So that's the traditional way that people work with this, and we want to translate this CLT to a general estimator. So we want to be able to have statements like this. We want to be able to multiply, let's say, I know that theta hat n converges to theta naught. I would like to have a sequence of numbers that goes to 0, multiplied here such that this converges in this distribution to something non-trivial, in which case we'll say theta hat n minus theta n, or this converges to theta naught at rate 1 over an. Okay, so we want statements like this for general estimators, in particular for the MLE. Okay, Does this make sense? Everyone remembers what a CLT was? So the CLT, you might not have seen it written in this form. This is how statisticians would write the CLT. Anyone remembers how probabilists would write down the CLT usually? CLT is the central limit theorem. How many people know what central limit theorem is?
It's that.
Okay.
Yeah, is it just what they write like X bar converges to a normal distribution with mean mu, and I guess with the one variable, the variance would be sigma squared over n.
Yeah, but that's not how they state it. So if you properly want to state it, you have to have a limit which is not dependent on n. So what I meant is usually they work with Sn, the sum, not the mean. So in probability theory, usually you work with the sum. So you would write something like Sn minus its expectation divided by the square root of its variance. This is standardized Sn. This converges to, let's say, in distribution to a normal with mean 0 and variance 1. It's a univariate case. Okay, and you can translate this to the average. So if you translate it to the average, anything that you can write in terms of a sum, you can translate it to the average. It would look something like this. In the univariate case, it would be just 1 here. Or it would be like root n divided by x bar n minus mu divided by sigma converges in distribution to normal 0, 1. So that's the statistics version. Let's see, stat version. It would work with x bar n. They're equivalent, but statisticians work with x bar n because it's like an estimator. So you get root hat n times this divided by sigma, converges in distribution to normal 0, 1. They're equivalent. So if you have seen the other one, you can easily translate it to this next one. But this also has the property that it shows you the rate of convergence immediately. Okay. So let's move on. So before we can prove results like this for a general estimator, we need some calculus to actually translate CLT results to other sort of scenarios with ease, just like you do, for example, develop a calculus for manipulating different differentials and integrations. And so you have the calculus developed like that. So you don't have to compute the derivative of every function from scratch. So if you know the derivative of a couple of functions, then you'd use the properties of the derivatives to compute like chain rules and stuff like that to compute new derivatives. So you can do the same for convergences in probability. So we're going to develop some of the, or discuss some of the properties, not necessarily prove them, and then use them to drive new limit theorems. So this proposition sort of summarizes most of the things that we need. So the first one is that convergence probability. So okay, so convergence distribution, I didn't talk about this, but we discussed this in a previous lecture, and I'll refer to you to that lecture. You can define it as convergence of CDFs at the continuity point of the limit CDF in the univariate case, but there's a more general version via convergence of anyone remembers the more general way before I say it? More general definition.
Was it like the expectation of a function converges to the same, so like the expectation of the, yeah. limit.
Right. So this converges to this as n goes to infinity for all f continuous and bounded. This would be equivalent to xn converging distribution to x. And you can take this as the definition in higher dimensions. This is easier to work with in certain cases because it doesn't require you to specifically specify or know the distribution, like the densities or things like that, which are a little bit tricky to work with, or CDFs, which are problematic in higher dimensions. Okay, so some of the properties are that convergence probability is stronger than convergence distribution. So whenever sequence xn converges to x in probability, xn also converges to x in distribution. Vice versa is not true. In fact, you can see from this type of definition that the sequences are not really converging to the limit. Only the distribution converges. So there is no real link. So here xn and x could be defined in different probability spaces. Whereas in converging probability, there is an intimate relation between xn and x. So you really are converging. You're defined on the same subspace, or sorry, same space, and so on. But in any case, so convergence in probability implies convergence in distribution, but not vice versa. Convergence to a constant, however, here this is a random variable in general, but if the limit is a constant, then you can say that it's going to be equivalent to convergence in distribution to the same constant. So convergence to the constant is equivalent. Whether you write it in distribution and probability, it doesn't matter. The next result is the continuous mapping theorem that says that xn converges to x if xn converges to x, and if f is continuous, then if I apply f to both sides, f of xn would converge to f of x. And this holds for both convergence distribution and convergence probability. So you can put p here, or you can put d. It would work in either case. Okay. And for the convergence and distribution, if you use this characterization, you can immediately see why this holds. Because if you apply a function, you basically get a composition with any continuous bounded function and compose with another continuous function. It's going to be continuous and bounded. And so immediately this type of definition would show that. You can use similar ideas for convergence and probability. But this is very useful for us because it allows you to translate one convergence statement to many via applying a continuous transformation. Okay, questions so far? Okay, so the next one is what I'm stating as Slutsky's lemma. Slutsky's lemma is actually a consequence of this, but I'm going to refer to this as the Slutsky's lemma because all the other things in the Slutsky's lemma sort of follows from this. And the idea here is that if I have a sequence x and converging in distribution to x, and a sequence of y and converging in distribution to a constant, then the joint distribution, if you form a sequence, let's say form a vector x n y n. This is a new sequence of vectors. By the way, all of them these could be vectors. So x n and x, they could be even matrices. So they're well defined. So convergence distribution and convergence probability well defined for vectors, matrices, any exotic object for which you have minimal. Let's say in here you have to have distances. If you go back to the definition, for this you just have to be able to define continuous bounded functions over them, and so you can think of them as vectors here. So I have this sequence of random vectors converging into a random vector in the limit, another sequence converging to a constant, and I formed this joint sequence. This would converge in distribution to the limit that's obtained from concatenating the two limits. So concatenating two converging sequences would lead to a convergent sequence. So this is not in general true if the second one is, if both basically are random variables. So you need at least one of them to be a constant. And that's the tricky part. I'll give you an example or a counter example where this fails if the limit for both of them is random. So the importance or significance of Slutsky's lemma is that if one of these limits is constant, then I can use that. And part E says, however, for the convergence probability, if you have a convergence in probability for two sequences, if you concatenate them, the result is going to converge in probability. So this doesn't have that limitation. So you can also see that in that sense, convergence probability is quite strong, okay, stronger than the convergence distribution. Finally, if xn converges in distribution, and you have another sequence x, y, n, whose distance to xn is going to 0 in probability, then yn has to converge in distribution to x as well. This is very useful in the sense that you know the limiting distribution of one sequence, and for this one, for example, you might be able to establish that xn minus yn basically converges to 0. That's what it is. You don't know the limit of yn, but you can show that the distance goes to 0 in probability, then you're done. So you know the limit of yn as well. For part C, the continuity needs to just hold on a set on which x lives. So if there is a set such that the probability that x belongs to C is 1, I need f to be only continuous there. This is useful, as we'll see. For example, if you divide by something that could possibly be problematic when the denominator is 0, as long as on a set on which my random variable lives, the denominator is non-zero, then it's fine. Yeah, this other one I'll already mention. So part D, the Slutsky, it's key that one of the limits is constant. Okay, I'm going to stop. Let you take a look at this and let me know if you have any questions.
Sorry, I have a question regarding part D. So here x is a random variable, right?
Yeah, potentially.
Yeah, so I guess this is what I don't understand, because if x is a random variable, the value of x is not fixed. So how yeah, so and C is a constant. So and it's basically states it's a converging distribution. So yeah, so if we can converge in distribution for some random variable, so what does that mean to converge in distribution to some constant?
So you could have asked this here as well. What does it mean to converge in distribution to a constant, right?
So that means the variance is smaller and smaller, something like that?
It's a little bit more tricky because convergence in distribution does not necessarily involve convergence of the moments. So you can't say, for example, the mean of xn converges the variance. In some cases it could, but your rough idea is the same. So the distribution gets, like, if it has a density usually gets narrower and narrower. Another way to see it is that it's equivalent to just convergence probability to a constant, right? If you want, what this is saying is, if you want to translate it more formally, xn converging in distribution to a constant is equivalent to saying that the expectation of f of xn converges to fc, right? If you use this definition that I have above for any continuous and bounded f. So this is valid, right? So the expectation converges, and this has that flavor that you mean. So it's as if there's no variation in xn in the limit. So can think of the distribution converges to a point mass, sort of. You can see there's, if the distribution, if it was like a random variable, then the limits would be different. So you'd have, for different f's, you get the different limits. So expectation of f of x would be different for different f's. But here, the limit is basically constant. So no matter what you apply, what f you apply, the limit is basically the same.
Yeah, so I guess here, so so based on this definition, I can only say that this is, for example, this is some unbiased estimator, but the variance can still be large. So
neither of them are true. The variance is intuitively going to 0, but neither that nor unbiasedness can be.
all right,
First, we're not talking about estimators here, so the bias is not well defined. But you can, for example, conclude that does not, for example, what I have to correct this. The limit is not constant, but the limit is like varies with f, but it's not. Yeah, I should have said that. But let's say what I mean is that there's no expectation involved in the limit. So this does not necessarily imply that expectation of xn converges to c, because the function that you have to apply here is unbounded. And this condition only guarantees convergence to continuous bounded f, not the identity function, which is unbounded. But in some cases with additional constraints, this would be true. So this, neither expectation of xn squared, these are all unbounded functions, unbounded continuous functions. So you need additional constraints. But your intuitive idea is the same, like correct. That the distribution of this is basically getting narrower and narrower around C. So as n goes into infinity, it's like basically converges to point mass at C. The variance drops to 0.
I see.
Okay.
Thank you.
Yeah, no problem. Other questions? Okay, so let's move on. So Slutsky's lemma has a consequence, which is often what is called Slutsky's lemma. So if I combine this part D with part C, I can apply a continuous function on the limit, and I get this is equal to f of x and c. So for example, if f of xy is x plus y, I conclude that xn plus yn converges the distribution to x plus c. Okay, or I can conclude that c times xn, or sorry, yn times xn converges to c times x, or yn divided by xn converges to, or let's say xn divided by yn converges to x divided by c. That's the actual Slutsky's lemma. So you apply these continuous functions to the limit in part D, and you conclude that if xn converges in distribution to x, yn converges in distribution to a constant, then these statements hold. And here for the last one, you need that basically the limit, because I'm applying this to the function y minus 1/2 times x, I need the limit to be non-zero here. So c has to be non-zero, in which case the function would be, so this function is continuous on the set of all xy's such that y is not equal to 0. Okay, and if c is non-zero, then the variable, the random variable in the limit was that this, with probability 1, this lies in this space on which the function is continuous. And so yeah, I'm good. And the way this is written is, this is from Asymptotic Statistics book by Van der Waart. Yn could be a matrix and x could be a matrix. So this could be a matrix inverse. This could be a matrix in the limit. And so these statements are all correct if you, and these could be matrix multiplications, as long as you respect the order in the limit. So all of this follows from just the basic argument that we have here applied to random matrices as well as random vectors. Okay, so that's the statement of the Slutsky's lemma. So if you have a sequence like this, converging distribution, you have another sequence, you can add them up, and then you get this interesting result. You can multiply them up, or you can divide. So any sort of continuous operation on the 2 would result in a valid statement in the limit. Questions? Okay, so one little statement here. If you recall, OP of 1, this is equivalent to saying xn. So xn is OP of 1 is a mnemonic for xn converging to 0 in probability. Okay, and this is equivalent to xn converging in distribution to probability. It is to 0 in probability. Sorry, xn converging in distribution to 0, because the 0 is a constant. So this Slutsky's lemma, you can replace this with, let's say if I have xn converging, xn is OP of 1, and yn is OP of 1. So the conditions of these two hold. So the limit of both are constant, and they're converged in probability, but they're also converging in distribution. So then I conclude that xn plus yn is also OP of 1, because the sum is also going to 0. So this is 0, this is 0. So the sum converges to 0. And so this is written mnemonically . Written mnemonically as OP of 1 plus OP of 1 is equal to OP of 1. Okay, so this is, if this is OP of 1 and this is OP of 1, if I add them up, I get OP of 1. So if you, once you get comfortable with this, you can manipulate these statements easily without needing to. I don't need to call this xn. I don't need to call this part yn. So you write down an expression, some part of it you identify this is going to 0 in probability. I'm going to call this OP of 1, and then there's another piece which is going to 0. It's going to be OP of 1. So the result is going to be still OP of 1 without naming them. So it's very useful in asymptotic arguments to quickly reduce a complicated statement. Questions, comments? We'll see examples of this in practice. Okay, so a simple example is, let's say, xn conversion distribution to z, a normal random variable, standard normal. Then I can conclude that xn is squared, conversion distribution to xn, the z is squared. And we know that z squared is has a chi-squared chi-squared distribution. So squaring a sequence of random variables that's converging to standard normal gives you a converging sequence in distribution whose limit is chi-squared. And this is just an application of what? Which one of these properties?
Part C.
Part C, yeah. So this would be continuous mapping by continuous mapping here. Okay, so here's a counterexample for the Slutsky's lemma, or part D. So what is the counterexample? So suppose you have xn, which is you have a sequence which is basically constant in the sense that all the elements are equal to x, and this x is uniformly distributed in 0, 1. So you sample a random variable uniformly 0, 1, and then you construct the sequence whose elements are all equal to xn. So this sequence, of course, converges in distribution to x. So xn converges in distribution to x. In fact, the distribution of every element of the sequence is the same as x. So this trivially is true. Now I'm going to construct another sequence, which is equal to xn if n is odd, and 1 minus xn if n is even. And the way that this works is that yn also converges in distribution to x. So why is that? Why this is true, that yn converges in distribution to x. Anyone? So what is the distribution of 1 minus xn?
Uniform distribution,
Why?
because you one minus a constant minus a uniform distribution is a uniform distribution.
Okay, yeah, so this is great. So this is exactly x. This is also equal 1 minus x. And so x is uniformly distributed, and 1 minus x is also uniformly distributed. So you can say this converges to uniform 0, 1. Sometimes you see that people write something like this, because convergent distribution just cares about the distribution of the limit. So instead of writing I converge to in distribution to a random array, we can say I'm converging, or the sequence is converging to a uniform distribution. This is also that. So this is also converging to uniform 0, 1, because every equivalent to saying that yn converges in distribution to uniform 0, 1. You also write statements like this, and these are valid. Because every element of the sequence, whether it's odd or even, has the same distribution, and the distribution is uniform, right? So no matter whether n is odd or no matter what n is, the distribution of xn is the same, and the distribution of yn is the same. They're all uniform. Okay, the idea is that xn and yn does not converge in distribution. And in the interest of time, I'm not going to ask you, I'm going to just try to argue it. The reason is, maybe I'm going to ask you, what is the distribution? So can you describe what the distribution of xn, yn is for n even and for n odd? And say if I plot xn, yn, as a point plot, what would it look like for different n's? So xn itself would be uniformly distributed on 0, 1. Yn itself would be uniform in 0, 1. But how about the joint? What would the joint distribution look like? So if n is even, xn, yn would just be xx. the way we defined it. So what is the distribution of xx? Anyone?
It's
Especially odd.
uniform in the 2D space.
You mean this?
Something like that, yeah. Yeah.
So it's going to be uniform in the square, 0 to 1.
Is it
times.
uniform on like the diagonal, like the line?
Okay, great. So it's going to be uniform on this line, not the entire. Because if the first coordinate is 2, the second have to be 2. So if I had drawn independent, so it was like x and y were independent uniform, then it would be uniform distributed in the square. But here it's going to be just uniform distributed on this line. So how about n even? X and y n would be x and 1 minus x. So what is that distribution?
The other diagonal.
Okay, great. So that would be this guy, uniform distributed on this. And you can see both of them have the same marginal. So the marginal for the first coordinate is uniform. The marginal for the second coordinate in both cases is uniform. So if you project it onto these two, for both you get uniform distributions, but the joint distributions are different. And the sequence alternates between these two joint distributions. It's like a sequence that alternates between -1 and 1. And so this cannot converge in distribution to anything. So this does not converge to x and x, and in fact does not converge to anything in distribution. So there's no convergence distribution in this case. Okay. So that's why you need the Slutsky's lemma in in Slutsky's lemma, you need one of the sequences to have a constant limit. Questions? Okay, so let's move on. So here's an example how you can use these basic properties to drive some interesting results. Suppose I have an IAV sequence, and we have the mean mu and the variance sigma squared. So I form the sample mean and the sample variance. This is the biased sample variance. Because we care about the asymptotics, it doesn't matter if you divide by 1 over n or 1 over n minus 1. For simplicity, divide by 1 over n. And so you can easily show that this sort of has the property of, so this is like an empirical variance. Variance under the empirical measure, and because empirical measure is a probability measure, all the properties that you have for the expectation holds in this case. So this is like expectation of x minus the mean. This is like expectation of x squared minus the expectation of x squared. So as long as you interpret the expectation as taking the mean with respect to the the empirical measure, then you can easily see that this statement has to be equal to this statement. That's one of the advantages of working with 1 over n here. So we have this expression for the sample variance, and this is for the sample mean. I form this so-called T statistic, which is a standardized version of the sample mean. So you subtract the mean of x bar n, and we know that, for example, we know that x bar n will have mean, which is mu, and variance. So what is the variance of x bar n? This is the minimum that should just be, after this course, this should come out like right away.
The variance of x over n.
Yeah, so sigma over n. So that's the minimum result of this course, is that you should be able to just say what the variance of x bar n is off the top of your head. So it's sigma squared over n. So if this is an estimate of sigma squared. So if I replace it with s squared over n, this would give me an estimate. So what I'm doing here is that I'm dividing by this square root of this, which is the estimate of the standard deviation of x bar. And so I'm subtracting the mean, dividing by the estimated standard deviation, sometimes called the standard error of the sample mean. And so the result is that if everything was Gaussian, you would have that this converged to, let's say if this was n-1, in fact. If everything was Gaussian, this would have a t distribution with degrees of freedom n-1, if you recall classical statistics. But here I'm not assuming any distribution, or here I'm not putting any assumptions on the distribution of this IID sequence besides the fact that we know that they're IID and they have like finite mean and finite variance. So the only thing I'm assuming is that the sequence has is IID, the same distributions for every element, and they have finite up to finite second moments. And the result is that I can use the previous properties to conclude that this T is statistic, in fact, convergent distribution to normal 0 line. And this also is true if you work with the T distribution. T converges as n goes to infinity, or the degrees of freedom goes to infinity, converges to a standard normal distribution. So how do we show something like this without distributional assumptions? You have to start from CLT and manipulate it using these properties and weak law of large numbers. So you basically have two basic statements, one convergent probability, the other convergent distribution, and then you can use these properties to combine these basic convergence results into more complicated convergence results. So how do we do this in this case? Again, I'm going to do it rather quickly in the interest of time. So we know that 1 over nx bar xi squared, this converges to the expectation of one of them. This is by the weak law of large number. And the expectation of one of them is the second moment, so it's going to be equal to variance plus mean squared. So then we also have that x bar n squared converges to mu squared. Okay, why is this?
We know x bar n converges to mu, and then we can use the continuous mapping.
Yes, continuous mapping and the weak law of large number for x bar n. I have this expression. So I know that the limit of this is sigma squared plus mu squared. I know the limit of this is mu squared. Can I subtract the two and say that this has the limit, which is the difference of the two limits? Can I do that? Can I say that s squared converges in distribution to sigma squared plus mu squared minus mu squared? Is that true?
Yes, by Slutsky.
Yeah, okay, so by Slutsky's theorem, because both of these are constant, at least need one of them to be constant here, both are constant. So this is Slutsky's theorem telling you that Slutsky's theorem tells you that this is true. So this converges into sigma squared. You can see it's an unbiased estimator, unbiased, asymptotically. This is consistent, right? So s n squared converges in distribution to sigma squared means that it also converges in probability. So it's consistent for sigma squared, i.e. consistent for sigma squared. I can take a square root of Sn squared converges to square root of sigma squared, again by Slutsky. So Sn converges to sigma as a positive square root. This is by continuous mapping theorem, not Slutsky. So I have Sn converges to sigma. So Sn is also consistent for sigma. Note that it's not unbiased, so Sn is not unbiased for sigma, but consistent for sigma. It's like asymptotic property. So you can see things are simplified in the asymptotics. So you don't have to worry about the fact that taking square roots sort of destroys unbiasedness. Just asymptotically, things are valid still. You get a consistent estimator of sigma. Now I can combine these. So the idea is that this convergence distribution to something like this. How can we argue this? So I'm combining this fact, this minus. I should have started a new page to not mess this up. So I know that root n x bar n minus mu converges to normal means 0 and variance sigma squared. So this is the CLT. And I also know that Sn convergence distribution to sigma from above arguments. So then I can say this divided by Sn convergence distribution to normal 0, 1, 0 sigma squared divided by sigma. And this in fact is normal 0, 1, can easily verify. So why this statement is true?
Still Slutsky?
Yes, Slutsky again. Slutsky's theorem. So you can see how useful this Slutsky's theorem is. So one of them is random, the other one is constant. I can still apply the result. And so this is the t statistic that we wanted. So you've shown that this t statistic in fact converges in distribution to normal 0, 1. And this is a distribution-free result. So we didn't make any distribution assumption, but I get an asymptotic distribution. And I can use this to build asymptotic confidence intervals for x bar n. So you can show that the probability basically that, let's say root n x bar n minus mu divided by Sn, this is bigger than 1.96. This probability converges to the probability that the normal distribution is bigger than 1.96, which is going to be something like that. So from this, you get that the probability that mu is in x bar n minus Sn divided by root n times 1.96 and x bar n plus Sn divided by root n 1.96. This converges to 0.95. So this is an asymptotic 95% confidence interval for the mean of any distribution that has finite second moments. So you didn't need to do some Gaussianity. So you can see how useful these arguments are, and it's fairly simple to drive this using the basic properties that we mentioned. So one of the usefulness of this is that these asymptotic distributions is that you can build asymptotic confidence intervals. In the sense that the probability that you're in this interval, the truth is in this interval, is converging to what you want. Okay, I'm going to stop here. Any quick questions? Okay, if not, we can continue in the office hours. I just have to warn you that I have to cut it short today. So we're going to start at 5 and end at 5:30. Sorry for the short notice, but if you want to please come early. If we go over a little bit, it's fine. But I'm trying to end it rather earlier today. So come in between 5 and 5:30, and let's try to wrap it up by 5:30. Okay, thank you. See you in about 10 minutes. Okay, goodbye.